In this lecture, we are going to have a look at the analysis of variance from the regression viewpoint. The analysis of variance is also known as ANOVA. We have already seen this identity before when we were trying to find the coefficient of determination small r square when it comes to a two-variable regression model. I hope you remember that it is known as capital R square when it is a multivariable regression model. So going back to that equation, we had seen that summation yi square, here yi means observed yi minus the mean y bar. Yi hat square, yi hat is the expected yi hat or the estimated yi from the mean, from its mean. And similarly, ui hat square is again deviation, intends to be deviation of ui hat from its mean, but by our CNLRM assumptions, mean of the error terms is equal to 0, right? Which is why we have not got a different deviation form and a different absolute form in the case of the last term. Now, summation yi square, or the variations in the observed yi, is called the total sum of squares. Summation yi hat square is the explained sum of squares. Technically speaking, it is the variations in observed yi which is being explained by variations in the values of x variable that we have taken in the regression model. Now, whatever variation is left to be explained is captured by the third term, summation ui hat square. It is also known as the residual sum of squares. So, the part of the variations in observed yi that cannot be explained by variations in x variable, that is known as the residual sum of squares. It is captured by the term summation ui hat square, or the variation in the estimated error term. The study of these components of TSS, or the total sum of squares, is called the analysis of variance. Generally, we use a table for studying the analysis of variance. The first entry in the table is the source of variation, or variation. Variation means deviation from mean whole squared, right? So you have your total sum of squares, that is the total variation in observed yi. It can be split into two on the basis of source of variation. One is due to regression. This is my explained sum of squares, that is variations in observed yi that is being explained by variations in the x variables. The remaining, the source of variation, is due to variations in the residuals, right? The associated sum of squares here is yi hat square, and here it is ui hat square. The total sum of squares is yi square. There is no hat in the third term because this is the total sums or the variations in the observed yi. Now, yi hat square, in terms of formula, I can write it as beta 2 hat square times summation xi square. It is small xi, so I am talking about deviation of xi from mean, capital Xi from mean x bar. Now, The total sum of squares, like I said earlier, in the total sum of square, your degree of freedom, now once again, associated with each sum of square is a degree of freedom. The degree of freedom is the number of independent observations on which the sum of squares is based, right? So the total number of observations in the sample is considered to be n. Your total sum of squares is, you are estimating the sample, computing the sample mean y bar to calculate summation yi square, and so you lose 1 degree of freedom. So your total number of observations is n. You lose 1 degree of freedom because you have calculated the sample mean y bar. So you are left with n minus 1 degrees of freedom. Your residual sum of squares is associated with n minus 2 degrees of freedom. This is because you have total n observations, and remember, if I can change the color, okay, remember your ui is yi minus yi hat, right? Which means it is yi minus beta 1 minus beta 2 xi. So to find summation ui or summation ui square, you have to estimate two values, that is beta 1 hat and beta 2 hat. And because you are computing these two estimates, beta 1 hat and beta 2 hat, you have lost 2 degrees of freedom, and you are left with n minus 2 degrees of freedom. So this will automatically mean that the explained sum of squares has 1 degree of freedom. Now remember, these values correspond to a two variable regression model. That is, when you are estimating something of the form, when your regression equation is of the form yi is equal to beta 1 hat plus beta 2 hat xi plus ui hat. So you have only one x variable and one y variable. This is a two variable regression model. Now if you divide the sum of squares divided by the degrees of freedom, what you get is the mean sum of squares. That's beta hat 2 whole square summation xi square divided by 1, so that remains the same. And here the mean sum of squares is summation ui hat square divided by n minus 2. You might remember that this is actually the formula of your sample variance sigma hat square. Now if you take the ratio of the two means of beta 2 hat summation xi square and the mean sum of squares of the residual, that is summation ui hat square divided by n minus 2, the ratio will follow an F distribution, where the numerator will have 1 degree of freedom and the denominator will have n minus 2 degrees of freedom. That is, F is the mean sum of squares of the explained sum of squares divided by the mean sum of squares of the residual sum of squares. I can write this as beta 2 hat summation xi square divided by sigma hat square. This statistics or this ratio thus calculated follows an F distribution where the numerator has 1 degree of freedom and the denominator has n minus 2 degrees of freedom. The reason we say it's an F distribution is because these sum of squares actually follow chi-square distributions, and when you have a ratio of two chi-square distributed variables, the ratio follows an F distribution. Again, the reasoning uses a few theorems based on statistics. We needn't go into so much detail. Just remember that when you take the ratio of the mean sum of squares, it will follow an F distribution. Numerator having the degrees of freedom 1 and denominator having degrees of freedom n minus 2 in the case of a two variable regression model. This computed F ratio, which is the mean sum of squares of the explained sum of squares divided by mean sum of squares of the residual sum of squares, follows an F distribution with degrees of freedom 1 in the numerator and n minus 2 in the denominator. It provides a test statistic to test the null hypothesis beta 2 equal to 0. So once you have calculated your F statistic, find the critical F value, calculate the F test statistic, from the table using the degrees of freedom information, find the F critical value, and if your test statistic is greater than this critical value or falls in the critical region, you are rejecting the null hypothesis that beta 2 equal to 0, and you are saying that beta 2 is statistically significant, which means that the variable associated with beta 2, that is xi, has a statistically significant impact on the y variable taken in the regression equation. Right? When it comes to a two variable regression model, checking based on or hypothesis testing based on the F test, based on the F statistic or the F test, is equivalent to the t test of checking whether beta 2 is statistically significant. Right? The difference between the t test and the F test is more evident and more prominent when it comes to three variable or multivariable regression models. There we distinguish between the t test and the F test, saying that the t test is employed for individual beta coefficients, whereas the F test is employed for checking the overall significance of the model. Right? Like I said, in the two variable regression model, your t test and your F test are are similar to each other, serving a similar purpose. But when you go into a multivariable regression model, something of the sort where you have more than one x variable, x1i plus beta 3 hat x2i and so on plus ui hat. When you have more than one explanatory variable, This would be an example of a 3-variable regression model. When you have more than this, more than one explanatory variable, the F test is used for testing the overall significance or the overall explanatory power of the model.